So today we start our chapter on linear equations, and you have probably seen linear equations before, but I'm hoping that you can make some new connections between some topics within linear equations. And the specific type of linear equation we're going to talk about today are situations that are constant increase and constant decrease. So really these are more like your real life situations that are constant increase and constant decrease. And I'm going to show you how to model them with linear equations, because really our focus this year is not just using linear equations, even though we will be doing a lot of practice with just graphing equations or just finding intercepts or something like that. But what I really want you to focus on is how these can be used to represent real life situations. So let's talk about what makes an equation linear. Well, here's the definition of equation. A linear equation is a function, so we've already talked about functions. This is a type of function that shows the relationship between two variables. Okay, so that's really nothing new. We've done a lot of things that show the relationship between two variables. But there are some specific ways that the two variables interact that make it a linear equation, some rules. And by the way, the two variables that I'm talking about here when I say it has to have two variables are almost always x and y. Technically, you could use other letters, but x and y are what you're going to see the most often. So here's what we know about x and y. They must be in separate terms. So you need to have like an x in one piece of the equation and a y on the other. They may be on the same side of the equation. Like, so for example, down here, okay, the x is separate from the y, so this one is a linear equation, okay? Over here, see how the x and the y are smashed together in one term? That would make this not a linear equation. So that's the difference between those two. These are separated by a plus sign. They might be separated by an equal sign, but they need to be separated by something. They cannot be located in the denominator of a fraction. And actually, that's related to this one, because if you were to solve it, while it's located in the denominator, you would end up multiplying by it, and then that would put them both in the same term. So, but this is just an easier way to think about it. So you can't have any variables on the bottom, and you can't have any exponents. Okay, to be linear, you want everything in the first degree, which means only the power of 1. So looking at these examples down here, let's decide whether or not these are linear equations, and we've already talked about some of them. This one here is sort of a textbook example of a linear equation. This is a yes. Okay, it's got x and y in separate terms, no variables anywhere, no fractions anywhere. Same thing with this next one, 2x plus 3y equals 9, also a linear equation. We've talked about that already. The x and the y are in separate terms, even if they're on the same side of the equals. I have an x and a y. This next one, though, 2x squared plus 12, is not a linear function because of that pesky exponent right there. Okay, that's actually a quadratic function because it has a power of 2. Okay, so that violates the last rule. Variables cannot have exponents. 4xy equals 11, also not a linear function because the x and the y are in the same term. 7 over x equals y, not a function because the x is on the denominator. And so here's what I was talking about with that. If I have 7 over x equals y, and I want to solve that, well, the first thing I would probably do is multiply by x on both sides. And I would end up with 7 equals xy or yx. And then you've got the same situation here that you did over here. The x and the y are in the same term. So that's why that's not allowed. Now, y equals 12. That might seem confusing to you, and you might initially say no because it doesn't have two variables. But technically it does, and we're going to talk about this quite a bit. I could rewrite this as 0x plus y equals 12. Right? Because I have no x's in there. And I don't have any exponents. The x and the y are in separate terms. So I'm totally okay here. So this is a linear function. And we'll spend a lot of time talking about what that type of linear function looks like too. Okay, so this is just some FYI about linear equations that hopefully help you conceptualize what a linear equation is. Okay? When I write a solution to a linear equation, you're used to thinking about solutions as being a single number. You're used to thinking about a solution being x equals 5. Well, you have two variables here. So now a solution is going to be a pair of numbers. Whoops, didn't mean to actually circle that. Okay, your solution is going to be a pair of numbers, which basically says when I put this number in for x, I get this number out for y. And that should remind you of when we talked about functions. When I put a number in for x, I get a number out for y. And so x is mapped to y. But there's a lot of different x's, okay? Which brings me right to my next point. There are infinite solutions to a linear equation because I can keep putting numbers in for x all day and then finding the y value that goes along with them. So when I take all of those x, y values and put them together and I put them on a graph, when I graph them, they're going to form a nice straight line. And that's why we call this a linear function. So this straight line right here relates to the word linear. That's why we call these linear, is because when I take all of the solutions, put them on a graph, it's going to form a straight line. And what's nice is when I draw that straight line, so let's say I have a linear equation and I find a couple of solutions, because you're never going to be able to find all of the solutions, right? There's an infinite number. But let's say I find this is a solution, this, and this is a solution. When I draw that line in there, okay, there's other points on that line. So this is a point on the line in between the two that I already have. There's a point up here. There's a point down here. All of those other points also represent solutions to the equation. So by drawing that line, I'm really trying to show all of the possible solutions to the equation. So this is asking us to find three solutions to this particular linear equation. And I just want to emphasize again that the solutions I'm looking for are going to look like this. Okay, they're going to look like ordered pairs. And there's an infinite number of them, so I'm being asked to find just three of them, because I can put anything I want in there for x and find out what it relates to with y. So I really want to emphasize that I can pick anything I want for x. Okay. Usually if you were here in class, I would ask you guys to pick anything, so you would believe me that you can pick anything. I'm just going to pick some numbers at random and find my solutions. Let me move this up so you have some room. Okay, so for example, I could pick x equal to 2. And so when I plug 2 in, I get y equals 3 times 2 minus 2. Well, that's 6 minus 2, which is 4. And so one of my solutions would be 2 comma 4. Okay, that's one solution to this linear equation. Now I can pick something else for x. Maybe I want to pick, oh, I don't know. Oh, that's a bad color. Sorry about that. Hold on. Let's pick x equal to negative 4. So I would do y equals 3 times negative 4 minus 2. Well, 3 times negative 4 is negative 12. And negative 12 minus 2 is negative 14. So another solution, and remember your solutions are written as coordinates, would be negative 4 comma negative 14. There's another solution. Last one I'm going to pick is 0, because I always pick 0. 0 is a good one to try. You're going to hear me say that a lot in this chapter. I'm going to say x equals 0. So y equals 3 times 0 minus 2. Well, 3 times 0 is 0. 0 minus 2 is negative 2. So this is equal to negative 2. And so my solution would be 0 comma negative 2. Okay, so that's how you find your solutions. And again, I emphasize, pick anything you want for x. I just chose numbers at random. You could have picked anything else and gotten other solutions because there's an infinite number. Okay, so one way to write a linear equation, and I really want to emphasize this is just one way to write a linear equation. You've probably seen this before, but you're going to see linear equations that look different than this. This is called slope-intercept form. And mathematicians are not super creative with their names of things. They call it slope-intercept because it contains a slope and an intercept. And we'll talk about what those are in a minute. So when you actually write this, if you actually write an equation in this form, I just want to show you that y and x are going to stay y and x. And then m will be a number and b will be a number. Okay, so when you write these equations, x and y stay put because that's where you're plugging in your values to find your solutions. And the m and the b will be numbers. So the m, just so you know, represents the slope. Okay, and is a measure of how steep the line is. Okay, the slope tells you, does your line look like this? Is it more flat? Is it backwards? Okay, all of those things are managed by the slope. Okay, so the slope tells you kind of how angled or how tilted your line is. Okay, the y-intercept, oh, didn't realize that popped up already. The y-intercept is this number that's here for b, and that b value tells you the point where the line crosses the y-axis. It's called the y-intercept because it's the place that the line crosses the y-axis when you graph it. So that's sort of like your starting point. Okay? So let's tear one of these apart. I'm giving you two equations, and from them I want you to identify the slope and y-intercept. And if you're not sure about that, look back up at here, or look back up here. The number here is your slope, the number here is your y-intercept. So in this problem, y equals 2/3 x minus 5. If I imagine that next to y equals mx plus b, the 2/3 is in the slope spot, and that 5, which by the way is a -5, is my y-intercept. In this next one, this is in my m spot, this is in my b spot. So -4 would be my slope, 2 would be my y-intercept. Okay, that might be a review of stuff you've seen before. So let's talk about this in terms of real life situations, because I told you that's going to be kind of our focus. Situations where you are starting with a certain amount and then changing at a regular rate. That can be represented with a linear function. That initial value, okay, the amount that you're starting at, and let me just throw out an example to you. Let's suppose your mom says, I'm going to give you an allowance of $20, and then I will give you an extra $1 for every dish you wash. I don't know that anyone's parents actually do that, but just as an example for the type of situation I'm talking about. That initial value, that amount that you're starting with, that is the y-intercept of your linear function. And the rate of change, that's the same thing as the slope. The slope measures how fast the line is changing. Okay? So let's look at an example here. An empty crate weighs 3 kilograms, so when it's got nothing in it, it weighs 3 kilograms just by itself. And then we fill it up with oranges that weigh 0.2 kilograms. Okay, so starting out, when I just have this empty crate sitting in a warehouse, it weighs 3 kilograms. That's my initial value. Okay, and then I'm going to add oranges to it, and for every orange, it's going to increase by 0.2 kilograms. That's my rate of change. Okay, so if I were to write this as an equation, just so you can see it, I would write y equals, my slope would be the 0.2, x would represent the number of oranges, by the way, and then I would add the 3 kilograms on because that's the weight of just the empty box. And that would give me my total weight. So that's how these functions work. So let's do an example together. And there's sort of two different ways to proceed through this. There is method 1, where you are just sort of reasoning out common sense what is happening here. 2 is using the rules and the algebra and the formula y equals mx plus b and plugging numbers into it. So whichever one of these works best for you is fine with me. So with method 1, if you read this problem, at the beginning of the month, Katie bought a 50-pound sack of wild bird feed. She put 2/3 of a pound of feed into the feeder each morning. So we're starting with 50 pounds, okay? So we're starting with 50. And then we're losing, because she's putting it into the feeder, we're losing 2/3 of a pound per day. And then if I plugged in my number of days, that would give me how much birdseed I had left at any given time or at any given day. So if I wanted to know how much birdseed would I have left after 5 days, I would start with 50. I would take 2/3 and multiply by 5 because I will have put 2/3 of a pound in every day for 5 days. Subtract from the 50, and that would tell me how much I would have left. Okay, so that's one method of writing one of these equations. Method 2, I could use that point slope, or sorry. Method 2, I would take the formula y equals mx plus b, and I would think about these in terms of my starting value and my rate of change. So my my rate of change, is going to be the 2/3 of a pound. And if I'm using up 2/3 of a pound, if I'm giving away 2/3 of a pound, that really means that I'm losing 2/3 of a pound. So I'm going to make that negative. My slope has to be negative 2/3. My y-intercept would be that initial value, which is 50. And that's positive 50 because I'm starting with 50 positive pounds. So my equation would look like this. Y equals, my m I said was negative 2/3 x plus 50. So again, it doesn't matter to me whether you think about it this way or think about it this way. These equations actually say the exact same thing. Okay, so either one of those is totally fine by me. Okay, so in this example, it's asking us to make a graph. And we haven't done a ton with graphing yet, but I am confident that you are able to do this. We have Al's temperature at 4 p.m. being 99.5. It rose at a rate of 0.3 degrees per hour for 6 hours, and then it stayed constant for 4 hours, and then it fell steadily by 0.4 per hour for 4 hours. I'm going to go ahead and scroll over to my graph. You'll want to keep looking back at this slide to get your information off of it. And I'm going to number my graph ahead of time, so you may want to pause the video when I flip the slide and number your graph before I start talking again. Okay, so you see I've got my graph set up already, and again, you can pause it now if you need to take a minute to get yours set up. I've got time down here along the bottom, and I counted where every line was 1 hour. I just only numbered every other line. And then going up the side, every line I have is 0.1 degree. Again, I only numbered every other one, but I really am counting by 0.1s. And let's take a look at what the problem says. The problem says L's temperature at 4 p.m. was 99.5. So I'm going to start at 4 p.m., 99.5 would be right there. It rose at a steady rate of 0.3 degrees per hour for 6 hours. So by 5 o'clock, it had gone up 0.3. 1, 2, 3. I'm going to put another point there. Okay. Another hour, it went up 1, 2, 3. Point goes right there. Okay, and I'm going to do that for 6 hours. So that's 1, 2, 3 over 1 up 3, 4 over 1 up 3, that's 5, and over 1 up 3, there's 6 hours. Okay, so I should be at 10 o'clock now, is that correct? Just checking. Yep. Okay, so that's 6 hours from 10 o'clock. I've gone up 0.3 every hour. So 0.3, 0.3, 0.3. Then it stayed constant for 4 hours. Constant means it's not going up or down. So if I'm here and my temperature is staying constant for the next hour, that's just going to take me to here. That's just going to move me along the hours, but it's not going to move me up or down in the temperature at all. So this is going to be like a horizontal line right here for 4 hours. So 1 hour, 2 hours, 3 hours, 4 hours. And then from there, it fell steadily by 0.4 degrees per hour. So from here, I'm going to go down 4 for the next hour. Okay, that's going to go right there. Then I'm going to move over another hour and go down 4. So that's going to be there. I'm going for 4 hours. Is that right? Yep. So 1, 2, 3, 4, and over 1. I'm going down 1, 2, 3, 4, and over 1, and I think that's 4 hours. So from here, 1, 2, 3, 4. Okay, and our temperature's not jumping like crazy, okay? And what I'm getting at is the decision, do we need to connect these points or not connect these points? Well, if my temperature was sitting at 99.5, and then when the clock hit 5 o'clock, miraculously it jumped to 99.8, and then the clock jumps another hour and it miraculously jumps to 100.1, that's not really what happens with a fever. There are temperatures all in between these points, so your temperature is rising constantly, and so there are other temperatures in between here. That means we do need to connect these points, and let's see how well I do this with a stylus. Not bad. Connect. Oh, it figures the horizontal line is what got me. And connect those all the way down, and that's what your graph would look like. So that graph would represent his temperature over time. Okay, that's all I have for you for today. Next up, this should help you with assignment 3-1, Lesson Master 3-1A.